Let's continue on compute. Right. So the next step, if we just go through virtual machine, and if you think about virtual machine, what it is, it's a abstraction of compute. Instead of the actual hardware, now you have an environment that's allocated onto certain hardware, still performing the same functionality of compute. Right? When you think about compute, what is compute? It can mean a metal box with some copper wires inside. It can be a combination of a CPU and memory, just like a virtual machine. Virtual machine, when you define it, is basically just CPU and memory and hard disk, right? But when you define virtual machine, you are still concerned about the physical details about CPU and memory. If you remember when we talked about provisioning the virtual machine, in that place, we have to pick. I need one CPU, I need two CPU, I need 8 GB of memory, 16 gigabyte of memory, etc. So you're still concerning about the details, physical details. If you want to further perform this abstraction of compute, you can think compute as a black box that can generate output when prompted with inputs. It's a black box. It's a Turing machine. You just give it some information, and automatically, magically, it's going to this black box will give you some answers. And that's the physical details are hidden. And when you think about the purpose of compute, the physical detail by itself, it is not important. It's truly not important. All you need to care as a business user is just the output, is a result. As long as the black box can generate the result you desire, who cares about the physical detail? Just like when I log into web browser to check my email, do I care where my email is stored? Is that going to make a difference that the email is stored in East US or West US? I really don't care, right? And so this is similar for all compute solutions. As long as you are getting the right data in the right time and with a proper performance, then that's perfectly fine. So that's what we call a further abstraction of compute. And there are there are these common types at this point. The types of compute abstraction, you can either remove the physical dependence in the constraints. This is what called the serverless, right? This is a further step down the virtual machine path, where you have a container or you have functions as service. And from functions as service, you can even see for functions of service, more physical details removed. Now let's completely focus on the black box idea of compute, which is I want to get the input, I want to get some output from the input I provide. Then that's what we call application programming interface or API. We will talk about these three concepts later in the later sessions. So starting with serverless. What is serverless? Serverless, the Azure definition of serverless, from the name you can see, it means no server. No server is serverless, right? Serverless computing enables developers to build applications faster by eliminating the need for them to manage infrastructure. With serverless applications, the cloud service provider automatically provisions, scales, and manages the infrastructure required to run the code. So servers are still run. It's still all the code are still run on servers. It's just that you don't see the server, you don't care about the server, and you are not worrying about those server, right? The serverless name comes from the fact that the tasks associated with infrastructure provisioning and management are invisible to the developer. The idea of a serverless starts with a container. To What is a container, right? The container, of course, it has multiple definitions here and there, but in this particular compute context, container is a specific abstraction of application. So applications these days must be able to run on multiple platforms, operating systems, right? One machine, one application need to be able to run on Windows, Linux, iOS, etc. Migrating these platforms is painful. I remember one of my first job a long time ago. those guys develop software and in Windows, and they try to migrate to Linux. It took them 2 years to do that, to have a successful Linux rollout. So it was painful to migrate your code between different platforms. What application want? But why would you? Would the application get so tightly associated with with the operating system? What application wants from OS are indeed pretty similar. It's a file access, memory access, configuration storage. These are things OS provide, but different OS have a different naming conventions or different format or different configurations. So when you are making these calls, it's very painful to get to get exactly the command that the OS asks for. If you cannot, then if you cannot generate those exact commands, then you cannot run on this particular OS. So the further virtualization is to have a container layer to simulate the functionality of a different operating system. Um, this may be a little bit confusing without looking at the chart, but before we deep dive, what does that mean? That means many functionalities are similar across different OS and their tool sets, right? Container layer is a one layer on top of operating system. It provides a common interface to those functionalities. As long as you have a container layer, you can say this container layer can run on top of any most of the operating systems, and you can submit the same request to the container. That container layer will convert your request to the proper command of the operating system that is running on, while the applications can keep their own configurations in the container. So it's about portability. You can port your application from here to there to there. And it's about efficiency. Once you have a portability, you don't need to spend so many hours, so many time, so many human hours in converting your code from one operating system to another, which brings agility that your code is faster to roll out and faster for delivery, right? Container, the key is by providing a insulation layer between application and operating system. Container makes user focusing on applications instead of operating systems. So here is a more intuitive, straightforward explanation. To the left is a virtualized stack we talked about, right? You have the hardware, you have a hypervisor. Then for each virtual machine, there's OS and application, OS and application. Each of this stack is one virtual machine. Here, the hypervisor layer is providing you with the isolation between OS and hardware. Now, for a container stack, there's one more layer which is containers layer. The container layer on top of the operating system. So for the same hardware, for the same virtual machine, remember this is a virtual machine. It can also be one virtual machine or multiple virtual machine, but basically, on top of each operating system, you can run a container layer, which hide the detail of the operating systems from the application. That application, each application will run in its own container space. That container will handle operating systems functionality. When application requires when application requires operating system functionality, it calls the connectors in the container. And the container context operating translate that request to local OS, local operating systems command. So it looks like as if application is directly running against the local operating system, but it's actually making its own call, just that there's the translator working in between, which is the container. So each application is packaged into an image. Now that's an example of how the same word can be used in multiple places. We just talked about image for a virtual machine. And that virtual machine image is about the state of a hard disk, right, with all the details of operating system. This image, container image, is have a similar usage pattern, where it's packaged and stored a package. It's a stored package of containers definition, applications definition. This container image contains the pseudo OS, which is the layer of interface that simulates OS. Application can contact this OS, and this pseudo OS will translate your OS demand into the local OS's demand. Then the next thing is the library supporting framework that your application will need, and your application's code and the executable and the configuration information. So here's an illustration of how you will run a container. You will store your image, your container image, your container definition, your application code, everything inside what we call the container repository. When you want to run a container, you bring this container into a container environment in your local virtual machine, Now, you need to have this container runtime in your virtual machine of OS. This is the container layer that we were talking about. This is the container runtime. You will bring your image from the repository into your container runtime. Your application will run here. Let's say your application issues some OS command. No matter what OS it is, it will get into the container. Container will translate this into the local operating system's command. So that means your application can run in multiple places, in many different places, under many different operating systems without you're considering which OS it is going to be running against. So container is such a useful tool. It's so useful in application that Microsoft and basically all the cloud providers, Google and Amazon too, are trying very hard to promote this container ecosystem. So for Microsoft, it starts with the Azure Container Registry. This is where you save your container image. And once you have the image ready in Container Registry, you can bring this up to several different ways of running container, and notably container instance, container app, and the Kubernetes service. Uh, you also have the web app for container function and the service fabric, but so far, these three, the container instance, container app, and the Kubernetes services are designed to run container. So they are optimized for container execution. So it's generally recommended to use these three to run container. The others can also run container, but there's no problem with that. It's just that the maintenance may be a little more complex than those container instance and container app and the Kubernetes service that are specifically designed for container. The difference between these three is a container instance is a single instance. It can launch containers with a one single machine, or with one single within one single machine, and not interfering anything else. Basically, if you look at the history, Microsoft is relatively late in this container space. So when it realized that container is the important trend, the other providers already have a really mature container services ecosystem. So Microsoft tried to cut short and roll out this container instance, which is a very simple, quick and simple and dirty way of running a container in the environment. Basically, it's just giving you a virtual machine, and you will run your instant container on that virtual machine. But this rush out solution turned out to be pretty successful because it's simple. Because it's simple, it's so developers love it. If you have like a short application, you need to run. You don't want to set up all the crazy things, all the configurations to run your configuration, right? To run your container, right? So if you can have something really simple and a lot of things are pre-defined for you, that's easiest and that's the best option. The And because it's simple, it also have a performance gain. It does not need to go through multiple layers of configuration and networking. So that's why container instance usually is considered more efficient. So because of these two, simple to implement and more efficient, container instance still have a, although it's probably the oldest container service in Azure, it still have a lot of presence. And then there's this container apps. Container apps is more like modern apps, and you can define many things like scalability. You can define many things like availability, these kind of things, and the connectivities among containers. So it's more complex than container instance, um, but it definitely provides more information, more services, and more functionalities. And finally, there's the Kubernetes service. Kubernetes is the open source standard on how to run and manage container. It's much more complex, but it's much more function. It has much more function. You can easily deploy and scale containers on Kubernetes. And most importantly, Kubernetes is open source. So you can run the same Kubernetes command on different service providers like Google or Amazon or Microsoft, and you can expect the same result. There's no ambiguity behind it. Like for other services like container app or container instance, if you use like infrastructure as code, you have to rewrite your deployment. You need to adjust your way of deployment if you want to deploy those to Amazon or Google. But for Kubernetes, you do not need to rewrite your practice. You can simply do the same thing in other cloud service providers, and you can expect the same application to be up and running and behave the same way.